Welcome to the Deep Dive, the show that unearths the hidden stories behind the world we inhabit. We spend our lives surrounded by incredible structures, from the sleek skyscrapers that pierce the clouds to the ancient temples that have withstood millennia. Even the simple home you're listening from right now.
hmm
But have you ever truly paused to consider what literally holds it all up? I mean, beyond the walls and the roof, what about the very ground it stands on?
It's a profound question, isn't it?
Hmm.
We often marvel at what's visible, the architectural grandeur, the finished product. But the true story, the immense planning, the historical wisdom, the engineering brilliance, and the sheer human effort often lies beneath the surface, both physically and conceptually.
Yeah, like under the ground.
Exactly. It's like admiring a magnificent tree without understanding the root system that anchors it, feeding it, and allowing it to reach for the sky. Without those roots, it simply can't stand. And in construction, those roots are the foundations, anchored in the earth itself.
Exactly. And that's our mission today. We're taking a deep dive into those foundational layers, quite literally, focusing on the fascinating and high-stakes world of geotechnical engineering, the science of soil, rock, and foundations.
Right.
We're going to explore how builders, from ancient times to today, have wrestled with the challenge of the ground beneath their feet. It's a journey into the unseen decisions and diverse disciplines that ensure our built world doesn't just look good, but actually stands.
And it's a crucial one. What lies beneath the earth itself is arguably the most important, yet often overlooked, part of any building. We'll be celebrating the experts who translate the hidden language of the earth for architects and structural engineers, providing the critical insights that truly hold our world together.
It's all about what you can't see, really.
Precisely. This isn't just about what we see, it's about making sure the part you can't see is robust enough for everything else to succeed. Investing in understanding that unseen part, the geotechnical aspect, is probably the most fundamental risk management you can do in construction.
Okay, let's start by digging into the echoes from the past. It's truly remarkable how much of what we consider foundational design today has roots stretching back to ancient ingenuity, often driven by an intuitive understanding of the ground. How did early builders establish these fundamental rules, sometimes almost instinctively?
It's incredible to consider that even without the advanced scientific language and tools we have today, early builders were keen observers and experimenters. They intuitively grasped principles that are still utterly valid.
Like knowing what worked through trial and error.
Exactly. And careful observation. Take Vitruvius, for instance. He famously observed that the Doric column's proportions were inspired by the human body specifically, the foot being 1/6 of the height.
Oh, I've heard that.
Now, this wasn't merely an aesthetic choice. It represented an early pursuit of structural fitness and beauty, seeing an inherent balance in the human form and applying it to building elements that had to stand firm against gravity. It's a foundational idea that links structural stability, how it meets the ground, to harmonious form.
So it wasn't arbitrary, it was deeply connected to what they understood about the natural world, including themselves, and the inherent stability of a well-proportioned form, which is crucial for anything sitting on the ground.
Absolutely, and you see this evolution, this adaptation of ideas, even when faced with challenging sites. Think
Yeah.
about Bernini at St. Peter's. He didn't design in a vacuum or on a perfectly blank slate.
Right, there was already stuff there.
Exactly. He had to integrate existing fixtures, like Fontana's massive obelisk, into his grand plan. He used trapezoidal and oval schemes, blending new aesthetics with some very practical constraints on the existing ground and structures. He was solving a complex, real-world, geotechnical, and aesthetic puzzle.
Yeah, working with what he had ground-wise.
Precisely. And Palladio, a master of inventive adaptation, pushed this further. When he needed designs for hillside villas, a very specific type of site that inherently involves complex interactions with the earth, requiring careful consideration of slope stability and foundations, he found no direct ancient or Renaissance precedents.
So what did he do? Just invent something?
Sort of. He looked at ancient monuments like Praeneste, not just as archaeological sites, but as a source of solutions for his contemporary problems. He saw the underlying structural and visual logic in ancient Roman terraces and adapted them for his own designs. This highlights a restless inventiveness, where he justified finding useful precedents by reinterpreting how structures could elegantly integrate with challenging topographies, challenging ground conditions.
That's a powerful example of how historical wisdom isn't just about looking back, but about drawing lessons forward, especially when you're dealing with the stubborn realities of a site, the dirt and rock itself.
You got it. And some forms, like the dome, have an incredibly enduring fascination. We can trace its lineage from ancient sources through Byzantine influence surviving in places like the baptistries and centrally planned churches of Tuscany, Pisa, Siena, Florence.
Right, those iconic Italian domes.
Yeah, and then popping up in Byzantine-influenced regions like Venice and Norman Sicily and churches like the Martirana or St. Mark's.
Mhm.
The shape just works, structurally,
Yeah.
especially managing the immense forces down to the foundation.
Makes sense. It distributes the weight evenly, right?
It absolutely does, both structurally and symbolically. A dome efficiently distributes weight, channeling it downwards, which is a fundamental consideration for its foundation, for the ground underneath.
Hmm.
And this structural understanding in early buildings goes beyond just grand forms. Greek architects, for instance, observed that a facade with perfectly vertical outer lines would actually appear wider at the top due to an optical illusion.
Wait, really? So perfectly straight looked wrong.
Yeah, visually wrong. To counter this, they designed with converging lines, inclining angle columns inwards and making intercolumniations narrower.
Wow, so they were already dealing with perception and optical correction centuries ago. It wasn't just about physical stability, but visual harmony, which of course contributes to the sense of stability for observers.
Exactly. And not only that, but the inclination of door and window jambs in Greek architecture, which prevented the illusion of a wider top opening, also served a static law by lessening the lintels bearing.
Ah, so it did double duty.
It was both an aesthetic correction and a structural advantage. An elegant example of form and function working in concert, right down to how the loads were distributed to the ground.
Clever.
Alberti, much later, formalized some of these observations into guidelines, suggesting building heights around a square should be 1/3 to 1/6 of the open area's breadth, and portico breadth equal to half the column height. These were attempts to codify harmonious proportions, but they also inherently implied considerations for how stable those proportions would be, especially in relation to the foundations and the ground.
Shifting from these design principles to the very tangible, let's talk about materials. What can we learn from the early choices and methods of construction and the craft that shaped them, specifically thinking about how they interacted with the ground?
What's truly insightful here is how practical and resourceful early builders were, intimately understanding their local resources, essentially, their local geology, what the earth gave them right there.
Like using local stone.
Exactly. We see the use of specific stone types, like freebed stone for facing and Ancaster stone, chosen for their properties and availability. They knew which stone could bear weight, which could resist weather, and which was best for facing, all of which ultimately impacts the foundational integrity. Materials weren't generic. They were specific to the task, the place, and crucially, what the earth provided.
And sometimes materials and structures adapted to entirely new purposes, which is a testament to their inherent robustness. You mentioned Constantinople.
Right. In Byzantine Constantinople, when churches were converted to mosques, offensive Christian decorations were simply whitewashed. It highlights the inherent adaptability of these structures and the materials themselves, transitioning across cultures and religions, often on the same established foundations. The core structure, the part connected to the ground, remained.
This really makes you wonder how much of our contemporary material science, especially in geotechnics, is simply rediscovering or refining lessons from this ancient practicality. It's a great point. Even with wood, they understood its properties and how it behaves when integrated into a structure, especially near the ground. We see methods like pre-shrinking to achieve stability, recognizing that wood is dried for many reasons, reducing weight, preventing fungi, increasing strength, permitting gluing. But the principal objective is to have shrinkage occur before the final product is locked in place.
So it doesn't warp later.
Exactly. They also understood juvenile wood's abnormal shrinkage properties, which often lead to defects like bow and crook. This knowledge, hard-won through centuries of experience, parallels the geotechnical engineers' need to understand soil behavior, how it shrinks, swells, settles before building on it.
So it wasn't just about cutting down a tree and sticking it in a building. There was a sophisticated understanding of how wood behaves and how that impacts the long-term stability of the structure, all the way down to its base.
Definitely.
And what about masonry? We hear about hollow concrete blocks for economy and reinforcement, and the traditional application of plaster and stucco. These are techniques that span millennia, aren't they? Absolutely. Hollow concrete blocks offer both economy and a means for reinforcement, and their stability and load-bearing capacity make them ideal for foundations in certain situations. Plaster and stucco have been used historically not just for finish, but for protection against moisture and erosion, further preserving the underlying structure and its connection to the ground. These are long-standing traditions of both building and protecting what you've built on the earth.
Let's delve into the artisans themselves and their tools. These weren't just brute laborers, they were highly skilled craftspeople, often intimately connected with the earth they were shaping, literally digging into it.
Indeed. George Agricola, writing way back in 1556, gives us incredibly detailed descriptions of the iron tools used by miners, specialized iron tools for splitting hard rocks in veins, wedges, hammers, and crowbars. These accounts emphasize the physical demands of the specialized nature of early craft, showing a nuanced understanding of tool design for specific tasks that were literally digging into the earth.
He really documented it all.
He did. He even describes the meticulous process of making cupels from ashes for separating lead from silver, highlighting the chemical knowledge and precision of early assayers. This deep empirical knowledge of materials and processes of the earth itself was fundamental.
That's incredible, the precision and knowledge involved, even then, for something as fundamental as extracting resources from the earth. And thinking about the great medieval cathedrals, it's clear the cathedral crusade relied on an army of skilled hands, including master masons and stonecutters, whose work often blurred the lines between mechanical labor and artistic sculpting.
Right, and these projects often started with monumental excavations for their foundations. You couldn't build that high without going deep first.
Makes sense.
What's particularly insightful here is how empirically these master builders worked. Villard de Honnecourt's sketchbook from the 13th century reveals their knowledge, which was empirically gained, yet geometrically precise. They preferred simple ratios like 1.2 or 1.3, partly because local measurements varied so much.
So simple ratios were easier to communicate.
Exactly. It made these proportions easily translatable regardless of the specific unit. This suggests a deep practical intelligence about how structures stand and how to transfer loads effectively to the ground, even without modern calculations or detailed soil reports. Even the use of horses on cathedral sites, protected by horseshoes, marks a historical period of maximizing animal strength in construction and land reclamation, often for the massive earthworks required for foundations. They used every resource they had to shape the ground.
Moving from these historical methods, which show an intuitive grasp of the ground, let's explore how architectural vision translates into reality today, facing significant engineering challenges that begin, crucially, with understanding the subsurface. How do architects shape space, balancing form, function, and aesthetic, knowing that their creation must stand firm on the earth?
What's compelling here is the sheer breadth of architectural philosophies, yet a common thread emerges: the pursuit of truth and purpose, deeply connected to how a structure interacts with its site, with the ground it sits on.
Like Frank Lloyd Wright.
Exactly. Frank Lloyd Wright, for example, defined good architecture as an embodiment of truth, beauty, and responsiveness to the environment and human needs. He was a vocal critic of superficiality, and his early work on the Winslow House marked a turning point toward his organic prairie school style, deeply connected to the natural landscape and the ground it rested upon. His designs were often literally emerging from the earth.
So, for Wright, it wasn't just about the visual, but about the experience and seamless integration with nature, and therefore the ground. Le Corbusier, on the other hand, comes from a different place entirely, calling for an architecture pure, neat, clear, clean, and healthy.
Yeah, quite a different aesthetic. He criticized the dismalness of our Western bazaar and emphasized organization and essential comforts, exemplified by his Bordeaux housing scheme, which he saw as an industrialization of the builder's yard.
So more about efficiency and order.
Kind of, yeah. Le Corbusier envisioned an urban-scale circuit board, almost, a computer in open air, driven by the objective of efficiency. Both Wright and Le Corbusier, despite their stylistic differences, were striving for an architecture that genuinely served human needs. But regardless of whether a building is organic or industrial, its fundamental stability starts with a clear understanding of the subsurface, the geotechnical conditions.
Right, it still has to stand up. And this emphasis on careful consideration extends to something as fundamental as orientation. Viollet-le-Duc noted the importance of orientation in Greek temples and medieval churches, driven by both religious considerations and artistic advantage. But beyond that, orientation also impacts environmental factors like sun exposure and wind loads, which in turn affect the structural design and thus the demands on the foundation, right?
That's right. It highlights how aesthetic and functional decisions were deeply intertwined, often stemming from cultural or spiritual beliefs, but always anchored by practical realities of the site, including the ground conditions. Palladio's work also exemplifies a rigorous approach to form, his recurring triadic composition with a central block and symmetrical flanking blocks.
Very balanced looking.
Exactly. A schema uniform across his plans and elevations reflects a strong classical and Venetian architectural tradition, creating a sense of balance and order that inherently contributes to a stable structural system, minimizing differential settlements in foundations. You need that stability when you're dealing with the ground.
Now let's turn to the invisible protectors of these designs: structural integrity and material science. These are the unsung heroes that prevent buildings from falling down, starting from the ground up. And this is where geotechnical engineering really comes into play.
It's the meticulous detail required that ensures a building's longevity and safety. For example, the critical role of concrete cover in protecting reinforcing steel from fire and corrosion cannot be overstated. Without adequate cover, steel can corrode, especially if there's moisture migrating from the ground, or it can buckle in a fire, compromising the entire structure, including the foundation.
And getting the concrete mix right is key too.
Absolutely. Equally important is appropriate bar spacing in concrete, ensuring that coarse aggregate can pass through easily during pouring, avoiding voids that would weaken the structural element. Imagine pouring a foundation with core bar spacing. You'd get weak points that could lead to catastrophic failure, perhaps uneven settlement.
Right. And the science behind everyday materials like Portland cement mortar is quite complex, yet absolutely fundamental for strong foundations.
Yeah, it's not just add water and stir. It cures by hydration, a chemical reaction, not just by drying. So the precise quantity of water is crucial for optimal workability and final strength.
Not too much, not too little.
Exactly. And there's a strict time limit, about 2.5 hours before hydration begins, after which unused mortar must be discarded. You can't just keep adding water to keep it workable. You'd compromise the very strength needed for the foundation.
This raises an important question. How often do we, on a construction site, compromise these fundamental material science principles, perhaps unknowingly, just to maintain a schedule or reduce costs? The temptation to cut corners on the unseen elements like foundations or proper soil compaction is always there.
It is a real pressure. We also see the concept of deflection as a critical structural design consideration. A 2x10 joist deflects significantly less than a 2x10 plank, even if they have the same theoretical carrying capacity.
Why does that matter so much?
Well, for flooring systems, deflection, or how bouncy a floor feels, is often the key performance criterion, more so than the actual load-bearing limit, because it has such a direct sensory impact on occupants. Nobody wants a floor that feels like a trampoline. This demonstrates that structural behavior, from the floor all the way down to the foundation reacting with the soil, is all about managing movement and loads.
I've definitely been in a bouncy room before, so it's not just about what breaks, but what feels right, what performs correctly. And wood, as we discussed earlier, presents its own set of challenges, particularly when it comes to moisture, which can impact its stability when used in foundations or near the ground.
Absolutely. Managing moisture is a constant battle, with differential drying causing stresses and defects like bow and crook, especially in juvenile and reaction wood. These are inherent properties that engineers and builders, including geotechnical engineers looking at soil moisture impacts, have to account for.
So you have to know your materials and your ground.
Exactly. The natural characteristics of materials, be it wood or the soil itself, dictate so much of the design and construction process. It's about working with, rather than against, those properties. Ignoring them is inviting disaster, especially with foundations.
Speaking of challenges and potential disasters, history is replete with examples of engineering feats, but also equally instructive failures, especially when the ground beneath was misunderstood or underestimated. Let's dive into some historical case studies, starting with Isambard Kingdom Brunel, a true visionary who often wrestled with the earth itself.
Brunel's career is a masterclass in audacious engineering, frequently pushing the boundaries of what was thought possible, especially in interacting with challenging ground conditions. He wasn't afraid to tackle tough geotechnical problems.
Like the Thames Tunnel.
Yes. From his early work on the Thames Tunnel, where he almost died due to flooding and ground instability, classic geotechnical hazards to his ambitious Great Western Railway, where he famously gambled to win or lose all on one bold stroke by insisting on the best road, not the cheapest. He understood that true quality, especially in a railway line or a tunnel through difficult soil, meant investing in the underlying structure, the earthworks, the foundations.
That's the mark of a true innovator, isn't it? His relentless pursuit of pushing boundaries.
It really is. He experimented with gas engines and faced immense technical problems, like designing pipes and joints to withstand pressures of 1,500 pounds per square inch in an era where 50 pounds was considered high. He truly was someone who dared to build castles in the air, as he put it, constantly seeking what was possible, not just what was easy.
But he knew those castles needed strong foundations.
Exactly. Whether it was steel or the ground itself, he knew the foundation was key. And this boldness, combined with the inherently dangerous nature of large-scale engineering, often led to public fascination, sometimes even morbid. Take the Great Eastern, for example, and the legend of the riveter's skeletons discovered within her double hull.
Oh yeah, that story. Is it true?
No, meticulous records later debunked this as impossible. Brunel himself conducted inspections, but it illustrates the public's enduring fascination with the hidden dangers and human cost of mega projects, many of which are intimately tied to the risks of working with and against the Earth, digging foundations, tunneling.
It speaks to the mystique of these massive undertakings and the incredible effort involved in their construction. But sometimes pushing the limits without adequate understanding leads to catastrophe. Consider the numerous boiler explosions on American river steamers in the 19th century.
A tragic example, with 27 ships lost in 1859-60 alone. These underscore the dangers of prioritizing speed and lightness over robust design in high-pressure systems.
And the lesson is,
These failures, while tragic, provided invaluable lessons that shaped future engineering practices, much like how foundation failures like the Leaning Tower of Pisa, perhaps the most famous example of geotechnical issue, teach us about soil mechanics and the absolute need for thorough site investigation. It's a powerful parallel. Underestimating the forces within a boiler is akin to underestimating the forces and behavior of the ground. Both can lead to disaster if you don't do your homework.
after all that vision and the historical lessons learned from overcoming obstacles or succumbing to them, we get to the intricate process of actually making it happen. That means orchestrating the build, which is where modern project management and coordination step in, with geotechnical input being absolutely critical right from the start. How has the evolution of project delivery transformed construction?
Well, one significant shift within the industry, which profoundly impacts how we approach complex elements like foundations, is seen in resources like the PMBO Guide, that's the project management body of knowledge. It transitioned from a process-based standard to one focused on principles.
Principles, not just processes. What does that mean practically?
It means emphasizing delivering outcomes, regardless of the specific approach used. This signifies a more holistic view of project success, beyond just checking boxes, and it means adapting to the unique challenges of each site, particularly the subsurface, the ground conditions identified by geotechnical engineers.
So it's less about a rigid checklist and more about achieving results, especially when dealing with the unpredictable nature of soil and rock, which sounds essential for geotechnics.
Exactly, and this ties directly into the necessity of tailoring approaches. Every project, every site is truly unique, so applying a one-size-fits-all methodology simply doesn't work, especially below ground.
Right, soil can change foot by foot sometimes.
Precisely. Tailoring project delivery approaches, methods, and artifacts to suit unique project characteristics is crucial. This is especially true for geotechnical work, where soil conditions can vary wildly even across a small site. The benefits are significant. More commitment from team members who feel ownership, a customer-oriented focus, and more efficient use of resources.
And it involves looking at the team, too.
Yeah, it involves evaluating attributes like trust within the team, the level of empowerment given, and the organizational culture. Does the culture support local decision-making, for instance, allowing the site team to adapt quickly to unexpected ground conditions found during excavation? Or does it demand external approvals for everything, causing delays while the hole sits open?
This sounds like a sophisticated dance, and it definitely requires a conductor. That's where the construction management role comes in, isn't it? They're the ones integrating all the pieces, including the critical information coming from geotechnical investigations, the soil reports, the foundation recommendations.
Yes. Construction managers, or CMs, are responsible for integrating all facets: planning, design, procurement, construction, and activation. Their role is to provide standardized expertise across these domains, managing scope, schedule, and budget.
And they need to see the whole picture.
Absolutely critical. They need to understand that an impact from a single design decision, or, crucially, an unexpected ground condition discovered during excavation, can have implications for the entire program. The CM needs that broad view to ensure geotechnical findings are properly addressed and integrated, not just filed away.
And sometimes projects are so complex or fast-tracked that they can't wait for a linear progression. That's where phased construction comes into play, which can be particularly useful for managing foundation work, I imagine.
Definitely. Phased construction is an incremental approach where each overlapping or sequential phase is treated as a separate project with a defined scope. This allows for flexibility and continuous design alongside construction, which is common in fast-track projects like the Crucell Bridge.
So you can start digging while design continues.
In essence, yes. It's a way to keep things moving efficiently, even when all the answers aren't available up front, especially when deep foundation work or extensive earth moving is involved. Each phase can build on the geotechnical findings of the last, allowing adjustments as you go.
Moving beyond the structure of project delivery, let's talk about the bedrock of construction management: time, cost, and quality. How are these critical elements managed in today's complex projects, particularly when the ground beneath is such a major factor?
Well, time-wise, the critical path method, or CPM, is the traditional backbone for project scheduling. It's essentially identifying the longest sequence of tasks where any delay pushes back the entire project's finish line.
And foundation work is often on that critical path, right?
Very often. Excavation, foundation installation, dewatering these can be major time sinks if problems arise. While the complex calculations for CPM were once incredibly tedious for humans, they are now ideally suited for computers. This allows project managers to identify the critical activities that dictate the project's overall duration. Complementing this is top-down planning and work breakdown structures, which provide a general frame of reference before getting into detailed job planning.
So you get the big picture first, then drill down. And cost control is obviously paramount for any project, and poor geotechnical planning or unexpected ground conditions can be a huge hidden cost.
Oh, absolutely, a budget killer. Cost management is a primary element of construction management. The level of detail in reporting systems varies based on the project's size and character, from simple for small projects to highly detailed for large, complex jobs. With modern tools like building information modeling, cost estimates can even be extracted directly at the discovery stage of design.
We'll get more into BIM later.
Right. But the key takeaway here is that investing in a thorough geotechnical investigation, upfront soil borings, lab testing, analysis while it adds to initial costs, is the most fundamental risk management practice in construction. It prevents far greater costs from unexpected ground conditions, foundation redesigns, or even catastrophic failures later on. You pay a little now or potentially a lot later.
Which brings us to quality and safety aspects that are literally enshrined in law, especially when it comes to digging into the earth and ensuring structural stability.
Yes. Building codes are essential for ensuring public safety and quality. The 2021 IBC, for example, provides pathways for new materials and construction methods to be approved, often verified by organizations like ICCES, ensuring strength, fire resistance, durability, and safety.
And for big buildings,
For high-rises, these requirements are particularly stringent, mandating non-combustible materials, enclosed shafts, and automatic sprinklers throughout the building, all built upon incredibly robust foundations that meet strict load-bearing criteria defined in large part by geotechnical analysis. Safety submittals and emergency response coordination are critical during the construction phase, especially for excavation, shoring, and working in trenches, all high-risk activities directly related to the ground. These are often addressed even before a project breaks ground in pre-bid and pre-construction conferences.
it's all about proactive measures, and none of this works without effective communication and engagement, especially when dealing with specialized information like geotechnical reports. It's no good if the report just sits on a shelf.
It's truly crucial. Effective leadership and communication are paramount, encompassing both formal and informal, verbal and written methods. Information is continuously collected through meetings, conversations, and electronic repositories, then distributed according to a meticulously crafted communications plan.
And the CM drives this.
The construction manager's role is not just to manage tasks, but to foster proactive participation from all stakeholders: owners, designers, contractors, subcontractors, and crucially, the geotechnical engineers whose insights are foundational to everything else. Everyone needs to be on the same page, especially about what lies beneath and what the plan is to deal with it.
Now let's look at the unseen challenges of coordination, which can often trip up even the best laid plans, particularly when dealing with the unpredictable earth. Subcontractor management, for example, creates a really complex web of relationships.
It absolutely does. General contractors frequently subcontract specific aspects of a project, creating a contractual web. For instance, specialized foundation work like deep piles, ground improvement, or complex dewatering is often handled by specific subcontractors with geotechnical expertise.
And that adds layers of risk.
It can. The project manager must be hyper-alert to lower-tier subcontractors, because if they aren't paid by their prime sub, they can place lands on the project, creating significant legal and financial complications for the owner. This definitely includes specialized geotechnical drilling or foundation installation firms. Keeping track of everyone involved is key.
And managing constraints, these hidden roadblocks, seems like a constant battle, especially when you're dealing with the earth, things you don't know until you dig.
This is where systems thinking is essential. The Last Planner System, or LPS, is one approach that aims to improve workflow reliability by systematically identifying and removing these constraints before they halt work.
What kind of constraints are we talking about?
Constraints can be physical, like needing rebar installed before concrete pouring for a foundation or needing specific excavation equipment on site. Or they can be informational, such as a crucial soils report being necessary before foundation design can even begin, or needing permits for dewatering.
So you clear the path ahead.
Ideally, yes. But what's insightful and a critical lesson from systems like LPS is that resolving constraints too far in advance can actually be detrimental. It might create unnecessary work in process or lead to rework if conditions change, like if further investigation reveals different soil properties than initially assumed. It's about finding the right timing, understanding the flow, not just solving problems as early as possible, especially when dealing with the dynamic realities of a construction site and its interaction with the ground.
From the intricate dance of project management, we leap into the future with the digital horizon, how technology is absolutely transforming construction and empowering us to understand the ground beneath like never before. And leading this charge, of course, is Building Information Modeling, or BIM. How is BIM changing things, especially for the geotechnical side?
BIM is truly a game changer, moving us far beyond traditional 2D CAD. What's remarkable is that BIM design applications capture design intent parametrically.
Parametrically, meaning?
Meaning the elements have intelligence and relationships, change one thing and related things update automatically. This drastically reduces coordination errors and provides a far superior 3D modeling environment. It's not just drawing lines, it's building a virtual model with intelligence. And this intelligence can extend to modeling the ground, the results of soil borings, and different foundation options.
And it's so much more than just a design tool, isn't it? It has these enhanced capabilities that touch almost every aspect of a project, including how we interact with geotechnical data.
Indeed. BIM integrates with other applications for rendering, energy analysis, structural analysis, and cost estimation. It also offers multi-user capabilities, allowing multiple project participants, including geotechnical engineers, structural engineers, architects, to coordinate their work simultaneously within the same model, fostering unprecedented collaboration.
So everyone sees the same thing.
Ideally, yes.
Mm-hmm.
This shared 3D model becomes the single source of truth for design collaboration, allowing designers and builders to work out constructability problems as design progresses, even modeling different foundation types and their interaction with the virtual ground, visualizing how they fit together.
One of its most powerful features, especially when dealing with complex underground infrastructure and foundations, has to be clash detection. How does that help with what lies beneath?
Oh, immensely. Clash detection is a powerful BIM process for checking interferences by searching for intersecting volumes in virtual true space. Sophisticated tools can identify various types of soft and hard clashes, not just a pipe going through a beam, but also a proposed deep foundation clashing with an existing underground utility line you mapped, or two different foundation systems encroaching on each other.
Finding problems before you dig.
Exactly, preventing costly surprises. Formats like OpenBIM collaboration format even allow for two-way communication to flag and fix issues directly in the original models, which is a massive leap forward in efficiency and prevents costly rework underground.
And BIM is expanding into the dimensions of time and cost with 4D and 5D capabilities, which must be invaluable for visualizing complex excavation and foundation work. Tell us about 4D.
Right, 4D BIM adds the dimension of time. 4D schedules dynamically link Project CPM schedule activities to the 3D objects in the BIM model. This provides a graphically rich, animated representation of planned construction sequences over time.
Like a time-lapse movie of the build.
Sort of, yeah. It's invaluable for phasing, coordination, and running what-if scenarios for earth moving, excavation sequencing, temporary shoring installation, and foundation installation. It makes the schedule come alive, allowing us to visualize the impact of ground conditions or construction sequencing choices on the timeline.
And 5D adds cost.
That's right. 5D cost management attributes resources and costs to every BIM model element, including foundation elements and earthwork volumes. This enables parametric and dynamic quantity takeoffs. So change the foundation design and the cost estimate updates automatically. This leads to far more accurate estimates for earthwork and foundation materials, shifting estimators' focus from tedious quantity surveying to more valuable cost analysis and value engineering.
But with all this integration, this sharing of complex data, there must be challenges, particularly around interoperability, right? Getting different software to talk to each other, especially with specialized geotechnical models or geological software.
This raises an important question for the future of digital construction. While BIM is powerful, a major constraint on the everyday use of advanced analysis tools is often the time-consuming manual data input required due to differing building geometry and data formats. Getting the geotechnical data into the BIM model seamlessly is still often a hurdle.
So standards are needed.
Exactly. The IFC standard, or industry foundation classes, and middleware tools like BS Procom Server are developing to achieve better interoperability between various design software packages, such as CAD, structural analysis, energy modeling, and hopefully more geotechnical software. This is crucial for integrating detailed geotechnical models directly into the overall building model, creating a truly comprehensive digital twin that includes the subsurface.
Beyond BIM, we're seeing this as part of a larger third digital revolution that's poised to transform construction and our urban environments in even more profound ways, including how we interact with the ground.
What's truly exciting here are the anticipated societal impacts of digital fabrication by 2025, where it moves from a nice-to-have to a must-have. This is driven by its ability to address enduring societal needs and enable local adaptation.
Like 3D printing.
Exactly. 3D printing is a key tool in this revolution, alongside other additives and subtractive fabrication methods. Imagine 3D printing custom foundation elements adapted precisely to unique soil conditions discovered on site, or using robotic systems for highly efficient, ground-specific earthwork and compaction. It's about empowering smarter, more responsive building from the ground up.
And this digital revolution isn't just about how we build, but how our cities themselves function. We're talking about smart cities and something called Hertzian space. What's that?
Well, urban big data, collected through various sensors embedded throughout the city, is allowing us to sense information on a tremendous scale, empowering citizens and optimizing urban functions like traffic flow or energy use. The built environment is becoming a physically habitable internet, a Hertzian space where architecture takes on a new kind of life through responsiveness and interaction with digital devices.
And how does that relate to the ground?
This can extend to sensors embedded in the ground and foundations, continuously monitoring things like soil moisture, temperature, settlement, or even seismic activity, giving buildings and infrastructure managers a deeper, real-time awareness of their interaction with the Earth. It allows for proactive maintenance and risk assessment.
That's a profound shift in how we understand our buildings and their foundations. And all of this is deeply intertwined with sustainable innovation, especially in how we utilize and respect the ground.
Absolutely. Whole system engineering, as advocated by figures like Amory Lovins, seeks to maximize benefits beyond just energy savings, considering all aspects of technology and its interaction with the environment. This means integrating buildings with local ecosystems and geological formations.
Like using nature itself.
Precisely. For example, using trees and vegetation for stormwater uptake and ground stabilization, reducing runoff and erosion, or designing living roofs for insulation and habitat creation, which also reduce stress on traditional drainage systems and foundations. These offer powerful synergies and cost reductions.
Working with the site, not against it.
Exactly. Component-based modeling using open-source languages like Modelica is also advancing building energy analysis (BEA) tools, allowing for more rapid prototyping and evaluation of sustainable systems that often interact directly with the ground, like geothermal heat exchange systems built into foundations.
As we wrap up our deep dive, it's vital to consider the human element and the societal impact of all this construction, especially how our understanding or misunderstanding of the ground beneath affects everything. Buildings aren't just inert structures, they profoundly shape urban life.
It's fascinating to consider how many different perspectives we have on the city, all of which implicitly rely on what lies beneath, on the foundations holding it all up. Louis Sullivan, for example, perceived the city as a power, but also as a contraction, density, limitation, and a cruel concentration.
Didn't sound like he was a fan.
He felt an antagonism with its restrictive nature compared to the freedom of the open, believing men had made the city when they were mad and it had mastered and confined them. This contraction and density he described inherently puts immense pressure on urban foundations and the ground below, requiring significant geotechnical consideration.
That's a very evocative description, capturing the push and pull of urban environments. And figures like Robert Moses, for all his monumental achievements in building infrastructure, also highlight the complex and sometimes contentious impact often built on or through challenging ground.
Indeed. Moses' vision for Long Island as a natural recreational community led to the development of parkways, which required massive earth-moving and crossing varied terrains. But it also inadvertently contributed to traffic problems in Queens by increasing flow without adequate linkages to city boulevards.
Unintended consequences.
Right. His strong, often confrontational leadership style enabled massive public works, often involving huge earth-moving operations and complex foundations for bridges and roads, but also sparked intense political battles and demonstrated the unforeseen consequences of large-scale planning, where the physical reality of the ground was often a major factor, dictating routes and costs.
Which brings us to James Jacobs, who had a very different view of urban complexity and how it integrates with its physical environment, its streets and sidewalks resting on the earth.
Jacobs observed that borders like those big highways Moses built tend to divide cities into pieces, in stark contrast to small parks and city streets, which she saw as knitting neighborhoods together and mingling people. Her work emphasized the organic, social fabric of urban life.
The life at ground level.
Exactly, and the importance of places that encourage human interaction rather than separation. The physical infrastructure, including the often invisible foundations and underground utilities, which require extensive geotechnical work, plays a subtle but critical role in either supporting or hindering this organic urban life.
And the very way we move through these cities is undergoing a radical transformation, again, often relying on complex infrastructure underground. The evolution of mobility reflects a broader shift in our relationship with technology and the urban environment.
The personal automobile was once a symbol of liberation, but in smart cities, we're seeing a shift towards a transportation portfolio. Real-time information platforms now offer diverse, shared options: city bikes, city cars, smart electric bikes, ride-sharing emphasizing ambient mobility, and a reduced ecological footprint.
And much of this relies on things we don't see.
Often, yes. This new mobility often relies on sophisticated underground infrastructure, from subway tunnels and utility conduits to charging stations embedded in streets, perhaps even new tunnel systems for autonomous vehicles eventually, all of which require meticulous geotechnical planning and execution. The city as a system is becoming truly integrated, offering new modes of inhabiting the physical city, and that physical city includes what's below the surface.
Finally, let's reflect on ethics and responsibility in engineering, because the people who build our world, especially those who understand the ground, the geotechnical engineers, carry a profound responsibility for public safety.
This raises an important question. What is the engineer's role in society, particularly the geotechnical engineer, whose work is often hidden but so critical? We see tempestuous disputes sometimes about licensing and civic involvement, with organizations like the American Society of Civil Engineers, ASCE, stressing the duty of engineers in civic work.
But conflicts can arise.
Sure, conflict of interest can arise when volunteers become clients, but the core message remains. Engineers, especially those dealing with public safety and the ground beneath our structures, have a deep ethical obligation to ensure robust, safe designs and construction. When a building fails due to a compromised foundation resulting from inadequate investigation or poor design, the ethical failure is often quite clear.
And when we think about large, complex systems, especially those interacting with the ground, it's easy to talk about side effects, but you argue that's a fundamental misconception, isn't it? There are only effects.
Absolutely. In systems thinking, there are no side effects. All effects are interconnected. It's a fundamental misconception to believe otherwise. For example, changing groundwater levels due to a deep excavation isn't a side effect of the project. It's a direct, interconnected consequence of working with the earth, potentially impacting nearby foundations or causing settlement.
So you have to think broadly.
You have to. Delays in feedback loops, like noticing settlement long after construction is finished, are critical determinants of system behavior, often leading to oscillations and unpredictability. Understanding these interconnections, especially within the complex system of the ground, is crucial for responsible engineering.
This reminds me of René Dubos's concern about undisciplined technology. where technology claims priority in human affairs and becomes a master rather than a servant? It's a powerful question. Are we serving technology or is it serving us? Especially when it comes to the ground beneath our feet, are we building despite the ground or with it?
It's a profound ethical challenge in an age of rapid technological advancement. The temptation to push boundaries, to build ever taller or on increasingly challenging sites, must always be tempered by a deep respect for the Earth's limits and a thorough geotechnical understanding. We need to ensure technology serves our understanding of the ground rather than allowing us to ignore it until it's too late.
And underpinning all of this, even in our high-tech world, is the soul of craft. You mentioned Richard, the carpenter.
Yes, Richard, a carpenter who repairs old houses reflects on the old-timers and how future carpenters will judge their work. This highlights a continuity of craft, a pride in workmanship that transcends immediate utility, and a sense of responsibility to those who come after. Right down to preparing a truly robust and thoughtful foundation, even if no one ever sees it again. That care for the unseen is vital.
We've journeyed from Vitruvius's Doric columns, inspired by the human body's inherent stability on the ground, to the parametric models of BIM, which help us visualize the unseen earth layers and foundation interactions. We've seen how the master mason's empirical geometry ensured stability, and how Brunel built incredible feats by understanding and tackling the earth, while others failed by ignoring its limits. What ties all these threads together through millennia is the persistent human drive to build, to solve problems, and to shape the world around us, always anchored by what lies beneath the soil, the rock, the foundation.
And what stands out, really, is that the most important part of a building is often the part you can't see. It's not just the physical foundations, but the foundational principles, the meticulous geotechnical processes, the site investigations, the soil testing, the analysis, and the unseen human efforts of those who translate the hidden language of the earth.
From the Greeks intuitively correcting optical illusions that affected stability.
Right, down to modern software detecting virtual clashes between a proposed pile foundation and an existing sewer line before a shovel even hits the ground. The unseen decisions, driven by a deep understanding of the subsurface, are paramount. Investing in that understanding is key.
So, as we look to a future where building technology rapidly advances and smart cities promise seamless integration, consider this. Are we becoming more attuned to these hidden languages of the earth, of design, engineering, and human organization, ensuring we truly understand what lies beneath? Or are we simply pushing the unseen deeper, making its impact even more profound and potentially overlooked, perhaps by underinvesting in the critical science of geotechnical engineering because it's not glamorous?
It's a crucial question. How can we ensure that as we build smarter, we also build with a deeper understanding and appreciation for all that truly lies beneath, giving our structures the strongest possible start by thoroughly investigating and respecting the ground they stand on?